Hey guys, welcome to example 5 of 9.2. We're doing basic factorial identities. To get started, let's look at the factorial identity that we need to do the proof. Now, the proof looks kind of intimidating at first, but it's actually rather simple if you just understand this identity. We got two of them over here, but they're really just the same thing, accounting for different starting points. So if you have an n greater than or equal to 1 or an n greater than or equal to 0, you use those identities, which I'll give you a numerical example of here. Pretend you have 5 factorial. So if n was 5, right, then we can do n times n minus 1 times n minus 2 times n minus 3 and so forth. So if I were to expand that out numerically, it's very simple. It's 5 times 4 times 3 times 2 times 1. What that identity up there represents is a partial expansion, sort of. So instead of writing 5 factorial as a full 5, 4, 3, 2, 1 expansion, I could just write the number 5, but recognize that 4 times 3 times 2 times 1 is 4 factorial. And that's kind of like a partial expansion, or it is a partial expansion there. And that's what this means. N factorial is n times the number right below it, so n minus 1 factorial, right? 5 times the number right below it factorial would be the same thing. They have a version for n is greater than or equal to 1 or n is greater than or equal to 0 because if you do 0 as your n and you minus 1, you're going to get a negative factorial, and negative factorials do exist. It's just that you get negative, of the same number. So we want to keep this identity for 0 or 1 as your smallest number. And notice if you use the 0 greater than or equal to 0 version, it would start saying that at n plus 1, you could do n plus 1, the next number down is n factorial, all right? So let's go ahead and use this basic factorial identity to do the proof. Now to do this proof, notice we have combinations here. N plus 1 choose 2 and n choose 2. Let's look at the actual formula because we don't have actual values to do a shortcut. So we're going to need to use the formula in its entirety. Formula is right over here. Now, there's n's and r's here, and the identity itself has n's. So I don't want to confuse you because this n is different than the n down there. So what I want you to do is look at this formula and think about this as the top number choose the bottom number. N is the top, r is the bottom. So n choose r, okay? So the formula goes top factorial divided by bottom factorial times the difference of top and bottom factorial. Again, here's the top number, here's the bottom number. The formula goes top factorial divided by bottom factorial times the difference of top and bottom factorial. Let's go ahead and apply the formula so we can actually do the identity or prove it. So I have n plus 1 choose 2 minus n choose 2 is equal to n for all integers n greater than or equal to 2. To prove this, I need to mess with one side only. So I need to make the left side, the combination side, equal to n, okay? So let's apply the formula. So the formula goes for the first part, n plus 1 is the top, so top factorial over bottom factorial times the difference of top and bottom factorial. Now I'm going to minus, again, same formula, top factorial over bottom factorial times the difference of top and bottom factorial equal to n. All right, so there is my formula applied. Now I can try to simplify. The first simplification is rather easy. It's n plus 1 factorial over 2 factorial. That's going to be, obviously, 1 minus 2 is negative 1, so n minus 1 factorial. So that first step was sort of trivial but necessary. Okay, now we're obviously going to be messing with the left side because it's way easier to simplify something than it is to, make n look like the left side, right? Just like your trig proofs from chapter 6 or 5, actually. You may be tempted right now to look at the differences of each denominator. So n minus 1 factorial, n minus 2 factorial, and you'd be tempted to multiply top and bottom here by n minus 2 factorial and top and bottom here by n minus 1 factorial. That could work. It's just you're going to create a lot of extra work for yourself. There's a much simpler way to do this, and it's understanding this, the partial expansions. Now, the question here is, when I showed you 5 times 4 times 3 times 2 times 1, I arbitrarily did 5 times 4 factorial, but I could keep expanding it and I say, well, that's 5 times 4. I want to expand it a little more. 3, I can stop it here and say, well, 3, 2, 1 is just 3 factorial, right? I arbitrarily stopped at 4 and went 5, 4, then 3 factorial. So I arbitrarily stopped at 3. Where should I stop here? Well, remember, I have 2 factorial on my denominator. Whoops. I have 2 factorial as my common part of my denominator, and n minus 1 and n minus 2 is my uncommon part. So it would be nice if n minus 1 just went away, right? It would be nice if n minus 2 just went away. So you know me, I love getting rid of denominators instead of forcing things to work. So same thing applies here. What can you say about n plus 1 compared to n minus 1? N plus 1 is a bigger number. What can you say about n factorial compared to n minus 2 factorial? N is a bigger number. So this is going to have factors in it that cancel out n minus 1 because this is a bigger number. This is going to have factors that cancel out this because this is a bigger number. So let's go ahead and expand n plus 1 factorial and n factorial until we've expanded it enough so that it does what we want it to do, cancel out the denominator. So let's expand the numerator, n plus 1 factorial. So if I want to expand n plus 1 factorial, the first number is n plus 1 itself. The next number below it would be n. Should I stop yet? Nope, doesn't help me cancel anything out. The next number below that is n minus 1. There's a match, right? So if I stop there and said, well, the remaining the factors would be n minus 1 factorial, right? I can now take my entire fraction and cancel that part out. Again, I understood that n plus 1 factorial was bigger than n minus 1 factorial, so I would have factors in n plus 1 factorial to cancel out n minus 1 factorial. All right, let's go to the second part. Second fraction, the numerator expanded out. N factorial expands to n times, the next smallest number is n minus 1. Whoops, n minus 1 like that. Still nothing to cancel out. Expand it again. The next number smallest is n minus 2. And there I can stop expanding and say, well, that's the end of my expansion because now I can cancel out my n minus 2 factorial. And now I have n plus 1 minus n minus 1 over 2 factorial, right? I want this to equal 1. That's going to be n squared plus n minus n squared minus n, plus n, sorry, over 2 factorial. And my n squares cancel out, so it's going to be 2n over, well, 2 factorial is just going to be 2. So n is equal to n. And I've proven that n plus 1 choose 2 minus n choose 2 is equal to n. And hopefully, even though there was a good number of steps, hopefully this wasn't too bad for you guys. All right, take care and good luck on your AP exams. No Math Excel assignment since I know it's AP testing week. All right, good luck, guys.